All right, problems 12, 13, and 14 on the kinematics. Let's go through them. 12. These are pretty straightforward kinematics problems, which means that we're going to be employing the kinematics functions. It's kind of a throwback to September. Starting from rest, the disk rotates with constant angular acceleration. If it takes 10 revolutions to reach an angular velocity of omega, how many additional revolutions are required to reach an angular velocity of 2 omega? So, there's a limited amount of information here. What we know is that delta theta is 10 rotations. Now, let's actually multiply that by 2 pi, and we're going to get our answer in radians. Delta theta is 62.83 radians. All right, that's what we know. And it starts from rest, right? So omega I is 0. Now, we don't know how much time this is going to take. We don't know alpha. And we don't know omega f. They just told us it was omega. So I don't have 3 out of 5. Some people will try to reason through these problems by using omega and staying in variables here. This is one of them where I'm not even going to bother doing that. Let's just say, for the sake of argument, we get out to some random number here, 50 radians per second. That's going to allow me to get an alpha and a time here. And it wouldn't matter what you choose here, so long as that we make the velocity of 2 omega 100. We have to stay consistent with the problem there. So if we go with this, right, we can get the other things here. So I'm going to go omega f squared, omega I squared, 2 alpha delta theta. The only thing I don't know here is alpha. 50 squared equals 0 plus 2 alpha delta theta, 62.83. We'll get alpha quick enough here. 50 squared equals 2 times alpha times 62.83. This is what I get for alpha. Alpha is 19.89. Now, if we chose a different value of omega, if we made up a different value there, we would get a different value for alpha. It's not going to matter, because in the next part of the problem, we need to figure out how many additional revolutions are going to be required to reach an angular velocity of 2 omega. So, if I'm looking at that, let's now make, we don't know delta theta. Omega I is still going to be 0. Alpha is going to be the same, but omega f is now going to be 100. So let's go delta theta, that's unknown. Omega I, 0. Omega f, 100. We'll double it. Now it's 2 omega. Alpha, 19.895. So we have 3 out of the 5. Let's solve for delta theta now. Probably use the same equation. 100 squared equals 0 plus 2. Alpha is now known. And we have here an unknown delta theta. So let's solve for delta theta here, see what we get. 100 squared equals 2 times 19.895 times delta theta. I get delta theta equaling 251.39 radians. Now, how many rotations is that? If I divide that by 2 pi, yeah, that's basically 40 rotations. So, initially we had 10 rotations, then we had 40. Actually on the answer key, I think the answer key says the answer is D, 40 revolutions, but the question says how many additional revolutions were there. So I guess the answer would technically be C, because we would need 30 additional revolutions above the initial 10 to get there. But either way, 40 revolutions occur. I think you get the point there. So I'll fix that. 13. I think this is a pretty straightforward one. We'll find out. Wheel rotates through 6 radians in 1.67 seconds. So delta theta 6, t is 1.67. And it's uniformly brought to rest. Omega f is 0. 3 out of 5. Ask me what omega I was. Looking at my equations, I'm going to go with this one, simply because that's my only unknown, omega I. So putting it in, we get 6 1/2 omega I unknown plus 0, 1.67 here. See what we end up getting. I get like 7.18, so I guess if we round that, the answer is 2. The answer would be E. You get, well, it's 7.19 actually. Pretty quick. 14. A wheel slows from 20 radians per second to 12 in 5 seconds under the influence of constant frictional torque. In these 5 seconds, the wheel turns to an angle of, you know what, that's actually going to be the same exact equation. Let's look at our variables. The only thing we don't know is delta theta here, right? Omega I is 20. Omega F is 12. The time is 5. So 1/2 20 plus 12 times 5. What do we get? 80? And is 80 the answer? Let's check. 80 radians is the answer. Keep in mind, I chose the equation here. It's going to get it done in one step. This is kinematics. All 4 equations apply to this motion. You could have easily solved for alpha, used another equation, and got your delta theta that way. Might take more steps, but it's still 100% legit. So keep that in mind. Whenever you're dealing with uniform angular acceleration, there's a pathway of least resistance, but doesn't mean you have to take it.